And welcome to the Supergen Offshore Renewable Energy Hub's annual assembly. I'd like to present to you our project funded by the Supergen Offshore Renewable Energy Hub Flex Fund called Autonomous Biomimetic RoboFish for Offshore Wind Farm Inspection. In this project, we've created an underwater autonomous vehicle called RoboFish that's used to inspect and monitor offshore renewable energy infrastructure autonomously. My name's Dr. Mark Post from the University of York Department of Electronic Engineering, and I'm presenting on behalf of our team, which includes my research associate, Dr. Wael Gorma, and from the University of Strathclyde Department of Naval Architecture, Ocean and Marine Engineering. We have our academic partners in this project, Dr. Ching Xiao, Mr. Marvin Wright, and Mr. Yang Luo. We also have several industrial partners who've provided us very grateful help in the process of this project. This includes from Pixie Limited, Andrew Durant, who's been extremely helpful in being able to create an autonomous underwater vehicle, as he's an authority on these matters. From East Coast Oil and Gas Engineering, Bodhi Sarkar, who's been very helpful in providing a power solution for RoboFish and battery management and recharging. And from the Offshore Renewable Energy Catapult, Mr. Alex Loudon, who's been extremely helpful in connecting this project to industry needs. Now, RoboFish was originally conceived as a biomimetic autonomous underwater vehicle capable of self-sufficient navigation around underwater structures, specifically for locating and monitoring structural damage to wind farms. It moves like a fish does, or like an eel, because it's articulated. It's made out of several separate body segments, like the ones you see here, and has a head on the front and a tail or a caudal fin on the back. Now, this allows it to have the agility of a fish. It can move very precisely. It can aim its head and move its body, and also doesn't have any propellers to get fouled on things. So it's very good in close proximity to other objects, and we've developed it into a prototype that could be potentially spun out as a commercial product because there's many different potential applications for this kind of a vehicle. Our key innovation when building the segments was the articulation. The problem with these kinds of articulated vehicles is they need to be watertight. In order to make sure that the system's completely watertight and can work for long periods without potential failure of seals, we developed a novel design for a magnetic joint that allows us to couple two segments together and allows a servo to rotate this external part here in each joint that will in turn rotate an internal rotor that will move the next joint connected to the body segment through this fork. This magnetic joint is a key piece of technology because it allows two segments to be completely separate. It also allows us to use 3D printing technology, and we've put stainless steel rings to allow us to put electronics and batteries inside the fish while keeping the system watertight under high pressure. And this is built out of ABS, and we've been able to very successfully get completely watertight 3D printed parts made. Now, as a modular system, of course, we need to use modular software and hardware architectures. Each module is a completely self-contained system. It has its own battery, it has its own microcontroller to be able to manage itself, and it has a communication system. So in the segments, we use an STM32F417 microcontroller here, which runs the servos. It has an inertial measurement system on it, a balance control unit, depth pressure sensor, and some external interfaces we can use for connecting other things to each segment. But it communicates with the other segments in RoboFish using Ethernet. And we're only using 4 connectors for Ethernet, so it's up to 100 base T Ethernet. But this 100 megabit Ethernet, we can send power over using a similar system to power over Ethernet, where differential pairs can carry DC current. So this power over Ethernet allows us to use only 4 wires for both communication and for charging the batteries from a single docking port on the front of RoboFish. Now, the head of RoboFish has a more powerful microcontroller on it. It's got a Xilinx Zinc, and the Xilinx Zinc is a system on a chip that includes an FPGA, floating point field programmable gate array, fabric that allows us to build accelerated algorithms. In this case, our accelerated algorithms are primarily for vision. So we have 2 camera ports on the zinc board that we developed, the carrier board. And we're only using 1 camera right now, but we can accelerate our algorithms by using FPGA Fabric, and we also have the capacity to accelerate inspection algorithms for in situ inspection and analysis of what we see while we're navigating around a structure. For communications outside of the RoboFish, we have an acoustic modem, which allows us a low-rate telemetry and for remote control, so we don't need to have wired operation to RoboFish. We also have an acoustic rangefinder that allows us to detect the range to whatever it is the cameras are seeing. So it allows us to get a rough depth estimate for anything that we are mapping and anything that we're looking at. I've mentioned we have a docking port. This is also designed around Ethernet, and it's designed so that we can connect with our partner ECOG, East Coast Oil and Gas's subsea power hub, which you see here. And the subsea power hub is an underwater generator that allows us to recharge the RoboFish. So once we get autonomous docking working, we can theoretically have RoboFish running indefinitely as it can recharge itself. Now, of course, teaching RoboFish to swim is also an important task. Our partners at the University of Strathclyde, Naval Architecture and Marine Engineering Department, have developed a very high fidelity model of swimming vehicles, or swimming fish, that you can see here. And what they've done is they've developed computational fluid dynamics models of RoboFish that we use to create the control algorithms that will actually move the joints. And based on these high fidelity computational fluid dynamics models, we can determine what joint movements we need to achieve a certain speed and to achieve a certain turning radius. So several different swimming gaits are possible, and this allows us to have very high agility. We don't have propellers that get fouled on things, and we have very high efficiency in the placement of where we can put the head for docking and for inspection purposes. Now, of course, it's not been an easy year for anybody to do testing outdoors. Originally, we'd planned to run RoboFish at the ORE Catapult facility in Blythe and to be able to test it in our lake at the University of York. Neither has been easy, unfortunately, as we've been under lockdown most of the time. But we have managed to get this prototype, the RoboFish prototype, which has been completed and 3D printed, out into a small lake that we have at York in December so that we can just verify movement and water tightness. Now you can see we haven't quite got the swimming gait down now because we haven't had the opportunity to do testing. We also haven't had the opportunity to test the vision system outdoors very thoroughly, so we've been using canned data sets that have been pre-recorded from other missions underwater and from other locations. Now, we have managed to develop remote control of the RoboFish through this control panel that you see here, and we have managed to be able to do some underwater vision testing as well for underwater environments. So here you can see we can do both visual odometry with reasonably high accuracy, and we can also do a similar limited amount of underwater SLAM, simultaneous localization and mapping, using the orb SLAM algorithm. And that work is ongoing, but we've shown some very good results in the evaluation so far. So in the future, the main thing we need to do is make use of the designs we've built to program in better gates, to program better control, to finish implementing and testing machine vision, and to actually be able to get RoboFish out into a dock environment or an ORE environment where we can test it thoroughly. We also have plans to build smaller versions of RoboFish because we've had quite a bit of industrial interest, but we still need to focus a little bit on making it smaller so that it fits into smaller spaces. And a lot of the follow-on work is probably going to focus on building smaller RoboFish that we can use in small areas such as pipes. So thank you very much. I would like to thank again all of our partners. Particularly, I would like to thank my research associate, Wael Gorma, as he's done an incredible job. He has built the prototype largely himself in his own house because we didn't have lab access. And as you can see, it's worked out, well, swimmingly. I'd also like to acknowledge the massive amount of effort and skill provided by Mr. Marvin Wright, who took time out of his PhD to develop several iterations of our novel joint and came up with the magnetic joint design that's made RoboFish possible. And also, of course, I'd like to thank ORE Hub for funding us in the first place to make this research possible and to allow us to initiate our work into this domain of underwater bio-inspired robots. And we hope that many of you will be able to talk with us in the future about potential applications, improvements, and other ways that we can use underwater bio-inspired vehicles like this. From all of our team, we'd like to thank you, and we hope that we'll be able to talk to you more in the future, and please send any questions or comments or suggestions that you might have our way. Best regards, take care, cheers.